Hello and welcome to this session on impact-based forecasting for heat waves. This module focuses on how heatwave forecasts can be strengthened by moving beyond meteorological values alone and considering the likely consequences for people, communities, infrastructure, and key sectors. The aim is to understand how heat risk can be monitored, communicated, and acted upon in a timely and practical way, especially within the Caribbean context and in support of early warnings for all. By the end of this session, participants should be able to understand the main components of an early warning system and explain how impact-based forecasting applies to extreme heat. Participants should also be able to identify key monitoring and forecast products that support heatwave impact-based forecasting in the Caribbean, and apply a basic impact-based forecasting workflow to anticipate likely heat impacts using a case study. A key point to keep in mind is that impact-based forecasting shifts attention from meteorological thresholds alone to real-world consequences and practical actions. An early warning system is an integrated system that combines monitoring, forecasting, risk assessment, communication, and preparedness activities. Its purpose is to help people and institutions take timely action before hazardous events cause serious harm. For an early warning system to be effective, it must operate from end to end. This means that observations, forecasts, risk information, warning communication, and preparedness actions must all be connected. A warning is only useful if it reaches the right people, is understood, and leads to timely protective action. Impact-based forecasting is a forecasting approach that focuses on the potential impacts of weather, rather than only the expected meteorological conditions. It shifts the question from what will the weather be to what will the weather do. This approach combines hazard forecasts with information on exposure and vulnerability so that decision-makers can better understand who and what may be affected. For heat waves, this means integrating temperature, humidity, duration, nighttime heat, and the people or sectors most at risk. It is especially important because humidity, duration, nighttime heat, and vulnerability can produce severe impacts even without record-breaking temperatures. Heatwave impact-based forecasting includes several connected components. Hazard analysis examines extreme heat, heat stress, duration, nighttime minima, and ventilation. Exposure mapping identifies people, infrastructure, outdoor workers, schools, agriculture, tourism, and aviation operations that may be affected. Vulnerability assessment considers age, health status, housing quality, access to air conditioning, urban heat effects, and water access. These components are then used to predict possible impacts, such as health outcomes, service disruptions, productivity losses, and stress on crops or livestock. Finally, effective communication and response are required so that warnings lead to agreed actions. In heatwave risk assessment, the hazard refers to the characteristics of the heat event itself. This includes intensity, duration, timing, and probability. Key elements include maximum temperature, minimum nighttime temperature, humidity, heat stress, weak winds or poor ventilation, and cloud cover. In the Caribbean, important drivers may include anomalously warm sea surface temperatures, subsidence and ridging, dust or aerosols, and suppressed convection. These factors can combine to produce persistent heat, elevated humidity, reduced cooling, and increased potential for heat-related impacts. Exposure refers to who or what is located in conditions where the heat hazard is occurring. This may include people living in hot urban areas, inland valleys, or poorly ventilated spaces. It also includes outdoor workers, school children participating in sporting events, elderly persons, infants, and tourists. Important exposed assets may include hospitals, clinics, the power grid, water supply systems, transport networks, runways, and airport aprons. Understanding exposure helps identify where impacts are most likely to occur and where protective action should be prioritized. Vulnerability describes how susceptible people or systems are to harm. For heat waves, vulnerability may be linked to health conditions, age, housing quality, income, social isolation, and access to cooling. Coping capacity refers to the ability to prepare for, respond to, and recover from the event. This may include access to air conditioning, social support, public health measures, water availability, and community outreach. Risk increases when high exposure overlaps with high vulnerability and limited coping capacity. Therefore, the same heat event can have very different impacts depending on local conditions. Predicting heat impacts requires multiple sources of information. In situ observations provide temperature, humidity, wind, nighttime minima, urban hotspot information, and evidence of inversion conditions. Numerical weather prediction guidance, including deterministic and ensemble models, helps assess future temperature, humidity, wind, high pressure, cloud cover, and persistence. Satellite data can support analysis of land surface temperature, cloud or outgoing long-wave radiation, aerosol or dust conditions, and vegetation stress. Ocean data, including sea surface temperature anomalies, help identify marine influences on boundary layer warmth and moisture. Local climatology and seasonality are also essential for defining meaningful percentiles and thresholds. Heat stress metrics translate meteorological conditions into more practical indicators of human discomfort and risk. The heat index combines temperature and humidity and is often useful for public-facing communication. Nighttime minimum temperature is also important because it affects recovery from daytime heat stress. If nights remain unusually warm, heat stress can accumulate over several days. However, thresholds should not be copied blindly from one country to another. Different islands may require locally validated categories, such as caution, extreme caution, danger, and extreme danger, based on local climatology and observed impacts. Impact models help connect the heat hazard to expected consequences. A simple approach is to use a matrix that combines hazard category with vulnerability level to estimate likely impacts. More advanced approaches may use statistical or machine learning methods to link heat stress indices with health outcomes, energy demand, or other sectoral impacts. These models should also consider compounding factors, such as power outages, drought, poor air quality, dust, or concurrent disease outbreaks. The aim is to create consistent and defensible decision triggers that support timely action. An operational heatwave workflow can begin several days before the most severe impacts occur. During days 1 to 3, forecasters monitor for persistent signals, rising nighttime minimum temperatures, and increasing heat stress. During days 3 to 5, the event can be confirmed and diagnosed by assessing drivers such as ridging, subsidence, sea surface temperatures, ventilation, and dust. Communication should then begin, using targeted advisories, sector guidance, and language that can be adapted for common alerting protocol messages. Actions may include opening cooling centers, conducting outreach, and applying work-rest schedules. After the event, forecasts and impacts should be compared to refine thresholds and improve messaging. The Barbados heat episode from the 7th to the 15th of June 2023 provides a useful case study for applying the impact-based forecasting approach. This was a prolonged early summer period of extreme heat with elevated humidity and high heat stress. The synoptic pattern favored subsidence, stability, and suppressed rainfall, supporting persistence. A strong low-level trade wind inversion capped the boundary layer, limiting vertical mixing and cloud growth and helping trap heat and moisture near the surface. Warm surrounding sea surface temperatures likely enhance boundary layer warmth and moisture, elevating apparent temperature, including the heat index. From an IBF perspective, the key questions are who was at risk, which sectors were stressed, and what early actions were triggered or should have been triggered. Building from the Barbados heat episode, targeted messaging should translate the heat hazard into clear, practical risk information. The message should answer 5 key questions: what, where, who, so what, and now what. First, it should explain what is expected: high to extreme heat stress, with elevated temperature and humidity likely to persist for several days. Second, it should identify where the risk is greatest, including urban, coastal, and inland hotspots, as well as communities where heat exposure may be higher. Third, it should identify who is most vulnerable, including elderly persons, infants, persons with chronic illness, and outdoor workers. The message should then explain likely impacts, including higher risk of heat illness, reduced productivity and disruption, and increased energy demand. Finally, it should state what people should do now: hydrate regularly, find shade and rest, use cooling centers or cooler indoor spaces where available, stay informed, and monitor official alerts. The escalation timeline should move from awareness to preparedness to action, and then emergency response if conditions worsen. Communication should be treated as a full operational cycle, not simply as a public announcement. The process begins with monitoring, where heat conditions are observed and analyzed. Once the risk is identified, the alert should be issued using consistent message templates and clear alert levels: watch, advisory, warning, and emergency. These levels help communicate increasing impact severity, from be aware to act now. The alert should also be CAP-ready so that one consistent message can be distributed through several channels, including mobile alerts, radio, television, official websites, social media, email, SMS, WhatsApp groups, loudspeakers, and community notices. The dissemination chain should be clearly defined, moving from the meteorological service or official forecasting authority to disaster risk management, health, and energy agencies, then through media partners and community networks. Communication should also include two-way feedback so that reports from communities, clinics, utilities, schools, and response agencies can be integrated into decision-making. In this way, communication becomes a continuous cycle: monitor, alert, disseminate, respond, and improve through feedback. A response matrix links heat warning levels to specific actions. For Barbados, green conditions would represent normal seasonal heat and would require routine monitoring, daily forecast updates, and general heat safety reminders. Yellow conditions, or a heat watch, would indicate elevated risk and should trigger internal coordination, preparation of public messaging, notification of health and disaster risk management partners, advice to schools and outdoor work sites, and monitoring of vulnerable groups. Orange conditions, or a heat warning, would indicate high heat stress and should trigger targeted advisories, community outreach, hydration and cooling guidance, work rest measures, and closer monitoring of health and energy indicators. Red conditions, or a heat emergency, would require escalation of health messaging, welfare checks for vulnerable persons, possible modification or cancellation of outdoor events, emergency coordination, and the opening or extension of cooling spaces where feasible. Each level should have clear triggers, responsible agencies, and practical actions aligned with national standard operating procedures. After the Barbados heat episode, verification should assess both the meteorological conditions and the observed impacts. Meteorological verification may include maximum and minimum temperature, humidity, heat index, 2-meter temperature, station observations, model guidance, and reanalysis fields. Environmental verification may include satellite land surface temperature, sea surface temperature anomalies, suppressed cloud development, rainfall deficits, and evidence of persistent subsidence or atmospheric stability. Impact verification would require information from health services, ambulance or clinic records where available, electricity demand, outages, water demand, school or workplace disruptions, agriculture and livestock reports, tourism and aviation feedback, and community reports. If some of these impact datasets are not available, that should be documented as a gap. A post-event review should ask what was forecast, what impacts occurred, and whether the messages were timely, understandable, and actionable. This process is necessary for refining thresholds, improving warning levels, and strengthening future heatwave impact-based forecasting. The Barbados case demonstrates why heatwave impact-based forecasting is important for Caribbean small island developing states. Heat risk can develop through a combination of persistent high temperatures, humidity, warm nights, suppressed rainfall, warm surrounding sea surface temperatures, and local exposure and vulnerability. In the early warnings for all context, this case highlights the need to integrate observations, forecasts, satellite products, sea surface and land surface temperature information, local climatology, and sectoral impact data. It also shows that warnings must connect heat stress to the people, places, and sectors most likely to be affected. Through the VLab, regional partners can use cases like Barbados to build shared training materials, case study libraries, message templates, and operational workflows. The next steps should include defining locally relevant thresholds, developing standard operating procedures, testing warning templates, strengthening stakeholder feedback loops, and routinely verifying outcomes after heat events. This will help move Caribbean heatwave warnings from general awareness toward actionable early warning. The key message from this session is that heatwave impact-based forecasting connects the forecast to practical decisions and early action. Heat risk must be assessed through the combined lens of hazard, exposure, vulnerability, and coping capacity. The Barbados case shows the value of linking heat stress with sector impacts, targeted messaging, response actions, and post-event verification. Effective warnings require clear messages, defined dissemination chains, coordinated sector response, and two-way feedback from communities and agencies. As we move into discussion, the main questions are how these principles can be operationalized locally, which thresholds and actions are most appropriate, and what impact data are needed to improve future warnings. This concludes our session on impact-based forecasting for heat waves. The main point is that heatwave forecasting should not stop at temperature values alone. A useful warning should explain the expected heat stress, identify who and what may be affected, and support early action by the relevant agencies and communities. The discussion can now focus on questions, reflections, and how these concepts can be applied operationally within Caribbean heatwave early warning systems. Thank you. Gracias. Obrigado.